Hi, everyone. Thanks for coming. Thanks to the organizers for the chance to give this talk. Today I'm going to be talking about some highly theoretical ideas for scalable error protecting against certain types of noise, in particular thermal noise in universal adiabatic computation. Oh dear. Oops. Okay, so start off with the local Hamiltonian problem. So it's QMA complete to decide the ground state energy of a local Hamiltonian up to inverse polynomial precision. So producing quantum ground states can be as hard as the quantum version of NP. And the proof of this uses the idea of encoding universal quantum computation into the ground state of a local Hamiltonian, as Keisuke explained earlier today. Now, my question is, can this complexity of ground states also persist to finite temperature states? And a related question is, these history states that encode quantum computation, they're used in the proof that ideal noiseless adiabatic computation is universal. So can we make that construction fault tolerant? So what I'll tell you about today is a framework for combining these history states with a variety of circuit model error correction schemes, in particular self-correcting topological quantum memories. And this will provide a way to encode universal quantum computation in a metastable Gibbs state of a local Hamiltonian. So at a broad level, what the Hamiltonian will look like are constraints that describe the propagation of the circuit and also constraints that describe the check terms of the error correcting code. So, and of course the idea is that we want to begin in a perhaps noisy ground state of some initial Hamiltonian and interpolate to some final Hamiltonian. And the noise model that we consider is low temperature, but independent of the system size, thermal noise, and also some forms of intrinsic control errors on the local Hamiltonian terms. And the result will be that the final Hamiltonian will have a metastable Gibbs state in the sense of a self-correcting quantum memory with exponentially long lifetime. And the goal is for this metastable Gibbs state to yield the result of the computation after readout and classical decoding. And the Hamiltonian, of course, should be k-local for some constant k with bounded degree interactions to avoid trivial solutions, and also at most polynomially many terms in the entire Hamiltonian. So this is kind of the theoretical rules of the game, if you like, for giving a proof of principle with admittedly large overheads. So an outline of my talk. So there's actually quite a bit of background. I'll tell you more about universal adiabatic computation. And also, thankfully, there was an introduction to sort of the version of this that uses local clocks. And then I'll also tell you some background about self-correcting memories. And then I'll start to describe our construction. So we're going to find that keeping the circuit Hamiltonian local when there's a scalable code is going to really depend on the idea of transversal operations from the quantum circuit model. These transversal operations are going to demand that we use the version of history states that use these local clocks. And because there's no universal set of transversal gates for any quantum error correcting code, we need to combine it with additional tricks from circuit model fault tolerance. In particular, we're going to do classical post-processing, but we're going to include it in the quantum state itself. So it's coherent classical post-processing. And furthermore, because we have these local clocks and our qubits can sort of be staggered in time from one another, we'll have to discuss a solution that involves dressing the stabilizers in the quantum error correcting code. And so then I'll try to, so really what this is about is taking a fault-tolerant quantum computing laboratory, including the classical machine that you use to do post-processing and taking the 4-dimensional space-time view of that in order to build this Gibbs state. And then I'll include some material about the analysis of this Gibbs state of the final Hamiltonian. Okay. So actually, the problem of encoding quantum computation into ground states is already non-trivial because highly entangled states look maximally mixed with respect to local operators. So it was really a genius solution by Kitaev to repurpose an idea from Feynman that involves entangling the time steps of the computation with this additional clock register. And we already saw some of this earlier today, but basically you build a Hamiltonian that consists of these gate propagation terms and also some term that checks that you're in a valid input state. And to look at these propagation terms, the idea is that when we advance the clock one time step, we apply the unitary gate at that time step, and because it's a Hamiltonian, we also have to include the Hermitian conjugate. So how are these Hamiltonians analyzed? Well, the propagation Hamiltonian turns out to be unitarily equivalent to a particle hopping on a line. So you define a unitary that is diagonal in the time register basis, and essentially performs the circuit from the initial state to the final state up to that time. And when you conjugate the propagation Hamiltonian with this unitary, you're left with basically a Hamiltonian that describes a single particle hopping and just identities implicitly acting on the computational register. And because this is a diffusive random walk, this is the argument that, well, this equilibrates in time t squared, and this exactly solvable particle hopping has a spectral gap on the order of t to the minus 2. Now, how is this used in universal AQC? The idea is to begin in an easily prepared ground state, which will actually be the ground state of that initial term on the previous slide, and then annealing to the final Hamiltonian, which is the history state Hamiltonian we just described. So in particular, it's not diagonal in the computational basis as we normally consider in adiabatic optimization. This really is the more general kind of adiabatic computation. And of course, the runtime estimate, you can get it from the adiabatic theorem in the usual way. You do have to analyze the minimum gap as a function of S. So the final Hamiltonian is the one we just described with this 1 over t squared gap. But you can use a monotonicity argument to find that the minimum spectral gap actually occurs at the end of the adiabatic evolution. And as we just argued, this goes t to the minus 2. So this is essentially the proof that universal AQC can be done in time polynomial in n and the length of the circuit. And also just to mention, the Hamiltonians we've described so far may not look very physical, but perturbative gadgets have been worked out in order to do this universal AQC with 2 local Hamiltonians. So now a version of this construction that may be a little less familiar are these history states with local clocks. So now instead of propagating each of the qubits according to some global clock register, we're going to actually assign clock variables to all of our qubits 1 through n. And now the history state will be a sum over valid time configurations. It's a superposition, unnormalized here, but here's the time configuration and the state of the circuit up to that time configuration. So this was developed in part to make history state Hamiltonians much more realistic for, say, 2D universal adiabatic quantum computation, because you can now imagine a 1 plus 1 dimensional quantum circuit as represented by this here. So this direction is time, this direction is space, and this is what I call a time configuration. It's a state of all the clocks. So this can be found in this paper here, and it's a method for doing universal adiabatic quantum computation in 2 dimensions, where you take a 1 plus 1D quantum circuit and you lay it out this way. But now, instead of just a simple hopping particle, our Hamiltonian is unitarily equivalent to the diffusion of this string. So you can now imagine this string diffusing through this 2D square lattice just by local updates. Okay, so now let's talk a bit about self-correcting memories. So first, the easy version, the classical version, which are basically ferromagnets. So you can think of a repetition code as a ferromagnet, i.e. an Ising model. But in the 1D Ising model, thermal fluctuations can flip a droplet of spins, and this droplet can now grow with an energy cost that is independent of the size of the droplet. In contrast, in the 2D Ising model, the energy cost of a droplet grows proportional to the boundary of the droplet. And because of this, so at finite temperature, droplets of sufficiently large size will be suppressed by this Boltzmann factor because of this boundary scaling. And this is what leads to ferromagnetic order below the critical temperature in this 2D Ising model. And of course, this underlies the robust storage of classical information. So the lifetime will now scale exponentially in the size of the code block, that is the repetition code that this Ising model corresponds to. And we have hard disk drives that work at room temperature. So the quantum analog of these self-correcting memories are based on topological error-correcting codes. And this is because quantum codes require some idea of local indistinguishability. And so rather than the symmetry breaking order that we saw in the Ising model, so a topological error-correcting code you could think of as minus the sum of some stabilizer generators. And the archetypical example is the 2D torque code or the surface code, which is analogous to our 1D Ising model in the sense that pairs of anyons can be created and they're connected by a string, but sort of the energy cost of growing this string is independent of the length of the string. And so in the 2D torque code, these strings can wrap around. Thermal excitations will eventually grow these strings until they wrap around the system and perform some unwanted logical operation. But similar to how going from the 1D Ising model to the 2D Ising model obtained self-correction, we can go from the 2D torque code to the 4D torque code. And here the logical operators are two-dimensional membranes, and they now have a scaling energy cost, and so they become suppressed by this Boltzmann factor. And a major open question is whether you can have this kind of finite temperature topological order, a self-correcting quantum memory, in 3 spatial dimensions. That is still unknown. So now I'll tell you about an even richer kind of self-correcting quantum memory, and these are based on color codes. So in 6 dimensions, you can have a topological quantum memory based on these color codes, and basically the point of it is that it allows for universal local operations. So in particular, transversal gates. So a gate is, when you want to perform a logical operation, you want to build this out of local physical operations. And basically these 6D color codes have a nice set of transversal gates, and you can complete this set using just teleportation of Hadamard gates. So this teleportation requires only the ability to prepare logical X and Z eigenstates, measure logical X and Z eigenstates, and apply logical X and Z conditioned on those measurement outcomes. So basically with these codes, you can perform all these gates just by doing local operations on the quantum code, and then when you need to perform a Hadamard, you have to do logical measurement, post-processing, and maybe a logical correction. And this paper, Self-Correcting Quantum Computers, was presented in the standard time-dependent view of quantum computation. So not this time-independent view of history states, but really the goal was a proof of principle scheme that resilience to thermal noise is possible. But there are, in this work, brief interruptions to this metastable equilibrium when gates are applied. That's the price you pay for active control. Okay, so now I'll begin to describe, I'll describe how these ingredients are assembled together in our construction. So each logical qubit in the history state is made of several physical qubits, some number that scales with the size of the system, and each of these physical qubits is going to have its own time register. So just as in the classical case, both the computation and the code stabilizers are enforced by local Hamiltonian terms. So you can think of the Hamiltonian as consisting of the propagation terms and also sort of those code terms I talked about. But now both of these depend on the time configuration on which they act. So one of the main things we need to address is that the propagation Hamiltonian needs to, of course, consist of local gates, but also the code Hamiltonian should not fight against these local gates. So something about these history state Hamiltonians is that they're frustration-free. At least the final Hamiltonian is frustration-free. And if you think about it, if you're just performing local operations on some code block, then the code check operators could also frustrate those gates that you're trying to apply. So we need to work something out to kind of accommodate this propagation without frustration. And really the framework I'm going to tell you about could be applied to any or many different circuit model fault tolerance schemes, as long as you have local code checks and all your local operations and all your logical operations are implemented using local physical operations. So this 60 color code with transversal gates is a nice example, but is not really a necessary aspect. We'll get into a kind of simpler version later on. And then something I mentioned at the beginning, because this gate teleportation that we need in order to complete the universal gate set, because that uses logical measurement and post-processing, we have to include all of that as part of the history state as well, which is a pretty large type of overhead, but still only scaling polynomially. So these transversal operations, you can think of a gate that you want to apply on a logical qubit as just a tensor product of gates acting on the physical qubits. So in the best case scenario, these might just be one local gates, for example. But now, if you wanted to apply just a transversal operation of this form, you would run into the problem that if you tried to use a global clock, then you would have to apply a gate on every qubit at once. So we must allow the local clocks to be independently advanced by local terms. Now we also need to protect those clocks from getting too far out of sync when we turn on thermal effects. And so this propagation term, even if you're just applying one local gate, will also check states of the neighboring clocks. And then now the next challenge that arises is that advancing these clocks one at a time would violate the code Hamiltonian if we just use one of these standard code Hamiltonians. And so the solution to this is based on a version of dress stabilizers. So here the idea is that the stabilizers will also be connected to an interaction term that knows what time it is. Now this interaction term, notice that here we have the support of a single stabilizer, which is just some local operator, and we only check the clocks that belong to that stabilizer. And depending on the state of those clocks, we might be acting on a time configuration in which some qubits are ahead and others are behind. So the solution then is to rotate the stabilizers by the gates that are missing in order to basically bring all the qubits up to speed or slow down the ones that are getting ahead. And you could think of this as the space-time view of the advanced and retarded potential in electromagnetism. So furthermore, here, this kind of describes the one local gate case, but when you do a 2-qubit gate, this dressing is going to intertwine stabilizers from distinct code blocks. But that's okay, because what we do is we limit the staggering to some constant window. So even though your locality kind of increases very rapidly within that window, it's only constant. Okay, so this slide actually explains a lot of the overhead of why our terms involve a relatively large locality of interaction, but still constant. So now, normally when we think of circuit model fault tolerance, we think of actively measuring the system. But remember, you can always think of everything as unitary in some larger Hilbert space. So the idea here is to replace what would normally be projective measurements with coherent unitaries that put the result in a classical ancilla. Well, it's really a quantum ancilla, but will only be used to store that classical information. And each of our physical qubits then has to be measured by a classical wire. So the classical wire you could think of as a logical classical ancilla that is encoded in the repetition code. So the tip of the wire is very pointy in order to keep the interactions local and bounded degree. But then it grows like, say, a concatenated tree in order to become macroscopic in size and be able to support this kind of self-correction. So classical post-processing is global and takes polynomial time. So if you think about, so this entire slide is really about thinking of our normal quantum computing laboratory, including the classical parts, as some larger quantum system, right? And here, if you take this view, the quantum computation has to wait around for the classical post-processing to complete, but that's no problem. Okay, so this four-dimensional space-time view of active error correction, we want to consider the history state of a fault-tolerant quantum computer, which could be maybe a leading implementation would be a surface code connected to some classical computer. And instead of a code Hamiltonian, schemes like this depend on actively measuring and correcting the stabilizers. Right, we talked about in the beginning how the 2D surface code is not thermally stable, but if you actually actively measure and correct the stabilizer generators, then you can perform fault-tolerant computation. And what I want to observe here is that there's no energetic protection on the qubits in this system, but there is an energetic protection in the classical computer. And so really, active error correction is possible because we dump entropy from our quantum computers into classical self-correcting memories. And we can actually see this in the mathematical analysis of our model, which is that it suffices for the code Hamiltonian to just be a repetition code acting on, again, coherent classical ancilla. So basically, a thermally stable Ising model representing the classical ancillas and allowing the propagation terms then to ensure that the quantum computational register contains the correct result. So how can we analyze what I've described so far? So essentially, the entire Hamiltonian will be unitarily equivalent by this large global unitary we saw earlier to a Hamiltonian that decouples the propagation of this higher dimensional space-time clock membrane and a separate Hamiltonian that acts only on the ancilla. And so the idea is that, well, okay. Another thing is that we want to use symmetry to understand the distribution over time configurations. And schematically, you can imagine that you can put the computation on a circle. So, you perform all the gates and then you undo all the gates in order to make all the time steps equally likely. That's what you do with a global clock. It's a little more complicated, but essentially you want to use some overall symmetry to understand this distribution over time configurations. And so we want to now initialize our classical ancilla in, say, their logical 0 state, protected by this H code. And because this H code will just be an Ising model, let's say, we actually know that it has a metastable Gibbs state, at least in this rotated frame. But if there's no energetic protection on the computational qubits, then they will just be maximally mixed at the physical level. But again, because of H code, we'll be close to the logical 0 state on the ancillas. Okay, so now let's rotate back to the real frame. So when we do this, the diagonal elements of the thermal density matrix are going to be acted upon by this unitary. So you can see that we have both the encoded qubits and the encoded ancilla, and because this unitary represents the operation of a fault-tolerant circuit, it's going to coherently measure and correct the errors. So again, the correct operation of this circuit depends on pulling entropy out of the encoded qubits and dumping them into the encoded classical logical ancillas. And then finally, the thermal stability of the ancillas is actually unaffected by this global rotation. One way of seeing this, at least in the weak coupling limit, is that the Davies generators only depend on the spectral properties of the Hamiltonian. And furthermore, we can analyze intrinsic control errors in the local Hamiltonian terms because this global unitary W, there will be some actual version that's implemented and some ideal version, and this will be small because W is based on a fault-tolerant circuit. So these two unitaries have to be close together. So now, what I've described is entirely about the static version of the construction. So it's universal quantum computation in a finite temperature metastable state of a K-local Hamiltonian, and this, because we're connecting stabilizers in high dimensional codes, K can get quite large, but it's definitely less than 1,000. And now so this kind of exposes a link between a 4-dimensional self-correcting memory, from the history state of a 3-dimensional fault-tolerant quantum computer. So if we could design a completely planar fault-tolerant architecture for the circuit model, this would seem to imply self-correction in 3D. Now, some bad news, why did we focus on the static construction? Well, in terms of the dynamical preparation of this state, lower bounding the gap of this membrane propagation operator is an open problem in mathematical physics related to the surface growth of crystals. So, okay, we worked on that for a while, but it turns out that in order to obtain a tractable gap analysis, we're actually going to modify it to have a non-uniform distribution over time configurations. And then I think one of the big questions is, what is the benefit of applying this kind of scheme to smaller geometrically local architectures, even if they're not fully thermally stable? Thanks.
We have time for a quick question. Maybe not quick.
Could you say some more about what the noise model is? I understand you assume that it's a thermal bath, and you said something about Davies generators, but beyond that?
Sure. So basically that, and also control errors, percentage intrinsic control errors on the local Hamiltonian terms, at least in this part about the unitaries being close. But those are the two aspects of the noise model.
So in other words, it's crucial for the construction that you have a thermal Gibbs state.
As the environment. Or, so one way of thinking about this is that in the ground state, everything would proceed in the standard universal adiabatic way, right? So you don't need the bath necessarily to make it work. But in some ways, this entire approach was motivated by trying to generalize these history state ground states to a thermal version. So in a way, that was really the problem that we set out to solve. Yeah.
Let's thank Elizabeth.